A steam locomotive carries its own power plant with it. Fire, water, fuel, and machinery, all moving together on steel rails, in one machine strong enough to drag an entire train behind it. Nobody built that by accident. Every rod, tube, and valve had a specific job, and the machine depended on thousands of these parts working together in the right sequence. This is the story of how engineers turned a boiler, a firebox, and a set of wheels into the machine that built the railway age, using one locomotive in particular as the proof it could work at all. Stick around because the cleverest part of this machine isn't the part you'd expect. Before locomotives existed, moving heavy loads on rails meant horses, and horses have limits. Engineers needed something that could generate its own power, carry that power source along with it, and continuously turn that power into motion at the wheels. The basic chain sounds simple. Fuel creates heat, heat creates steam, steam moves pistons, pistons drive the wheels, making every stage work reliably at the same time inside one moving machine was the actual engineering problem. Before a single piece of metal was shaped, engineers had to answer a harder question first. What was this locomotive actually for? Passengers moving quickly, freight moving heavily, steep grades, yard switching. Each answer changed the size of the boiler, the number of driving wheels, and nearly every dimension that followed. Locomotives kept changing as that question was answered differently for different jobs. Stephenson's rocket in 1829 and Union Pacific's Big Boy in the 1940s were separated by more than a century of engineers asking that same question and arriving at wildly different answers. Construction started with the frame, the locomotive's skeleton. It had to support the boiler, the cylinders, the axles, and the running gear, while absorbing the constant force of thousands of pounds of machinery moving together at speed. Workers began with heavy structural members, positioned with precision, because a mistake here would compromise everything built afterward. The frame wasn't the impressive part of the machine. Without it, there was no locomotive to build at all. The boiler was the part that could make or break the whole locomotive. Picture it as a giant pressure vessel, built around the process of turning water into steam. Heat from the fire passed through the boiler and transferred its energy directly into the water inside. Building one meant shaping large metal plates and joining them precisely enough to contain steam under enormous pressure without failing. Boilers were subjected to pressure testing and inspection before entering service, because a failure in the pressure vessel could be catastrophic. Inside that shell, the firebox, tubes, and steam spaces all had to sit exactly where they belonged. A small mistake here didn't just hurt performance, it created a safety problem. Fuel burned in the firebox, producing the heat that turned the surrounding boiler water into steam. Water surrounded the firebox's important surfaces, so heat moved directly into that water instead of escaping uselessly into the air. Fuel varied by locomotive and era, wood in some cases, coal in others. Rockets specifically used a copper firebox and burned coke during its trials. The fireman's job mattered as much as any engineering decision on paper. Keeping the fire fed and keeping enough water over the firebox crown sheet was the difference between producing steam safely and producing a disaster. Instead of routing hot gas through one simple passage, engineers sent it through many smaller tubes running the length of the boiler, all surrounded by water. More tubes meant more surface area for heat to transfer into that water. Rocket used 25 small fire tubes, about 3 inches in diameter, and the multi-tube design greatly increased its heating surface compared with the single flue boilers used by earlier locomotives. The idea only grew from there. Decades later, Big Boy carried more than a mile of tubes and flues inside its boiler. The small tube became one of the defining secrets behind some of the largest machines ever built. The locomotive needed a way to actually deliver all that power to the rails. Not every wheel did the same job. Some supported and guided the machine. Others, the driving wheels, received power directly through the connecting rods. Their size and placement determined traction, speed, and how the locomotive's weight sat on the track. As locomotives became heavier and more powerful, engineers often needed additional wheels to support and distribute that weight. And more wheels meant a longer machine that struggled on curves. Engineers eventually solved this with articulated designs, letting sections of the locomotive pivot relative to each other. On Big Boy, the front driving wheel assembly was articulated, able to move relative to the main frame to negotiate curves the rest of the locomotive couldn't take in a straight line. Steam from the boiler entered the cylinders, where pressure drove the pistons back and forth. Pistons don't rotate on their own. Their straight-line motion transferred through connecting rods to the driving wheels, turning that motion into rotation. Rocket used 2 cylinders, one on each side of the boiler, each connected directly to the driving wheels. That was the moment the invisible force of expanding steam became something visible. Enormous wheels beginning to turn. Steam couldn't simply flood into the cylinders continuously. Valves had to open and close at precisely the right moments, admitting steam, cutting it off, then releasing the spent steam before the next cycle began. Without that timing, the engine wasted energy, and the pistons never produced controlled movement. On Rocket, the valve mechanism connected to eccentric drivers rotating with the driving axle. It was one of the least visible systems on the machine, and also one of the most essential. After steam pushed the pistons, it still had somewhere to go. Engineers routed the exhaust through the smoke box and blast pipe, where the escaping steam created a strong upward draft through the chimney. That draft pulled more air through the firebox, which made the fire burn harder. The harder the locomotive worked, the more exhaust it produced, and that exhaust fed back into a stronger draft for the fire. It was a feedback loop built directly into the exhaust system. Rocket combined this blast pipe design with its multi-tube boiler, and that combination helped establish a pattern that would shape steam locomotive design for generations. Eventually, every separate piece became one machine. The boiler went onto the frame. The cylinders and running gear connected. Pipes carried steam and fluid where they needed to go. Then came the cab, the controls, and the tender for fuel and water. None of it went straight to the rails. Boilers and mechanical systems were inspected for defects, leaks, and weak points, with the pressure vessel receiving the most scrutiny, since a failure there could be catastrophic. The bigger and more powerful locomotives became, the more demanding that inspection process grew alongside them. Robert Stephenson and Company built Rocket in Newcastle upon Tyne in 1829 for the Rainhill Trials, a competition to determine which locomotive design would run the new Liverpool and Manchester Railway. Rocket was the only locomotive to complete the trials, averaging about 12 miles per hour and reaching a top speed of 30 miles per hour. Its real significance wasn't the speed, it was that Rocket brought the multi-tube boiler and the blast pipe together in one working machine. Even Rocket kept evolving after its win. Within 18 months, it had been substantially rebuilt. Locomotive engineering wasn't standing still, even for the design that had just proven itself. A century later, the same basic idea had grown almost beyond recognition. Union Pacific's Big Boy locomotives, 25 of them built between 1941 and 1944, used articulated running gear to carry enormous length and weight around curves that would have stopped a rigid frame entirely. 16 driving wheels, a 150-square-foot firebox grate, more than a mile of boiler tubes and flues, a working weight of roughly 1.19 million pounds. Next to Rocket, it looked like a different species of machine entirely. Underneath the scale, it was still the same principle: burn fuel, make steam, control that steam, and turn its pressure into motion. What the steam locomotive teaches you. Lesson 1. The invisible systems decide whether the visible ones work at all. Valve gear and the blast pipe barely show up in a photograph of a locomotive, and neither one produces motion by itself. Without them working correctly, the boiler, cylinders, and wheels never functioned as one machine. Lesson 2. Proving a concept once doesn't mean the work is finished. Rocket won the Rainhill trials and was still substantially rebuilt within 18 months. Winning the competition wasn't the finish line. It was proof the design was worth continuing to improve. Lesson 3. The same basic principle can scale to an almost unrecognizable degree. Rocket weighed only a few tons. Big Boy weighed roughly 1.19 million pounds. Both ran on exactly the same underlying idea: burn fuel, make steam, control it, and turn it into motion. A steam locomotive looks like one enormous machine from the outside. It was actually dozens of separate engineering problems, solved individually, then assembled with enough precision that they behaved like a single machine the moment the fire was lit.